Good morning students. Today we are going to see application of CFT to square planar complexes. Up till now we see the application of CFT to octahedral complexes, coordination number 6. Now we are going to see the application for the square planar complexes, that is coordination number 4. We have already discussed the tetragonal distortion of octahedral complex. Let us discuss the limiting case of such a distortion. Let us say that the tetragonal distortion proceeds so that the ligands along the z-axis go away from the central metal ion. Let us say that the distortion eventually becomes so large that the ligand along z-axis go away from the central metal ion. That is, in practice, the ligands along z-axis are removed. This is a limiting case of tetragonal distortion. As a result of the coordination number becomes 4 and a square planar complex is formed. Thus, when we are going to study the square planar complexes, we have considered that there is no any ligand along z-axis in octahedral complex, and thus we have the such type of the presentation. The ligands along z-axis are removed. The interaction of the ligands along x and y-axis becomes the strongest with the dx square minus y square less. So with the dxy, and the least with the yz, xz and dz square orbital of the central metal ion. Due to this interaction, new energy differences along the orbital of the metal ion arises. First of all, the degeneracy of Eg orbital is removed. The dz square orbital becomes lower in energy and becomes more stable than the dx square minus y square orbital. At the same time, the threefold degeneracy of T2g orbital is also removed. As the ligand on the z-axis is removed, the dyz and dxz orbitals remains equivalent to one another, but they become lower in energy and more stable than the dxy orbital. If the ligand are strong enough, then the separation becomes such that dz square orbital becomes lower to xy orbital energy. See in the figure, there is such type of the orbital splitting leading to ultimate formation of square planar complexes, and sequence after the splitting, dx square minus y square have highest energy, then dxy, then dz square, and then dyz and dxz orbitals. Thus splitting will be occurs. The most favorable electron configuration for square planar complexes is that of D8 ion. For example, Ni2 plus, Pt2 plus, Pd2 plus, Au3 plus. Here the splitting is great enough to bring about pairing of all electrons. They are very high energy. Dx square minus y square orbital is left vacant. Figure shows here the splitting of D8 system. See, when there is a D8 system, in T2G there are 6 electrons and Eg there are 2 electrons. but after splitting, and the splitting sequence in square planar complex, that is the lower energy for dxy yz, then dz square, then increases for dxy, and then increases for dx square minus y square. Thus electrons after splitting, they will be get enter into 4 electrons in 2 orbitals, that is dxz and yz, 2 electrons in dz square, then remaining 2 electrons in dxy, and already dx square minus y square becomes empty or remains vacant. Thus, the low spin d8 complexes, you will have electrons in the dyz, dxz, dz square and dxy orbital, leaving the high energy dx square minus y square orbital empty. In the square planar complexes, increase of the ligand field strength only increases the energy of dx square minus y square orbitals. But as this is not occupied, the complex becomes more stable. Typical square planar complexes are NiCN4 2 minus, PD NH3 2 plus, AuCl4 1 minus, all having D8 ions or D8 system. In the 3D series, metal ion only very strong field ligands like Cn minus pairing in dxy orbital necessary for the stability of the square planar complexes. Whereas in the 4D and 5D series, metal ions, since the pairing energy of electron is low, even weak ligands like halide ions can bring about the pairing of electrons and gives the square planar complexes. Square planar complexes are also expected for D7 and D9 ions. In square planar complexes of D7 ions such as CO2 plus ion, the highest energy orbital is effect, and next to the highest energy orbital, that is dxy orbital, has only one electron. A square planar complex of Cu2 plus ion, D9 ion, will have only one electron in the highest energy orbital. In any case, there is some additional stabilization due to the additional splitting atom or accuracy of the lower energy orbitals. In square planar complexes, precise calculations of energy levels of d orbitals have been made, and the CFSE, crystal field stabilization energy, have been calculated. The orbitals are placed in such a way that dyz, dxz, dz square are lowered by 0.51 delta, 0.51 delta and 0.43 delta energies respectively. The dxy and dx square minus y square orbitals are raised by 0.23 delta and 1.22 delta energies respectively. In the following table, see the CFSE values for square planar complexes. Here we see the weak ligand field and strong ligand field, or high spin and low spin situations. See from D1 to D10. See, first we see in the weak ligand field, that is high spin complexes. D1 system CFSE is 0.51 delta, D2 system 1.02 delta, D3 1.45 delta, D4 weak field 1.22 delta, for D5 0 delta, for D6 0.51 delta, for D7 1.02 delta, for D8 1.45 delta, D9 1.22 delta, and for D10 again 0 delta. While in the strong ligand field, that is in low spin complexes, see the number of unpaired electrons. We know that for the D1 to D10 number of electrons are calculated here. We having the D1 system, CFSE is 0.51 delta square planar, D2 1.02 delta, D3 1.45 delta, D4 1.96 delta, D5 2.47 delta, D6 2.90 delta, D7 2.67 delta, D8 2.44 delta, D9 1.22 delta, and D10 there is the 0 delta square planar. The radius ratio plays an important role in the geometry of the complexes. See here, the radius ratio, radius of cation upon radius of anion, that is radius ratio, is greater than 0.414 required for the square planar arrangement, is identical to that for the octahedral complex. Since the octahedral complex is favored by the additional energy release from the interaction of the two extra ligands, the higher coordination number is expected. The square planar arrangement is shown only in case where the additional splitting of the level is most advantageous, or where the planar configuration is imposed by the geometry of the ligand. For example, Ni2 plus ion D8 system shows octahedral geometry when the ligand is NH3, that is, while the same Ni2 plus ion shows square planar geometry when the ligand is cyanide, that is Cn minus. So example is NiCN4 2 minus. The Cn minus ion or ligand is a very strong ligand and gives much more splitting of d orbitals than the NH3 ligands. Hence, there is a difference in geometry. The divalent ion of the metals copper, beryllium, manganese, iron, cobalt, nickel, and platinum many times forms tetrahedral complexes, but forms a square planar complexes with ligands phthalocyanine, because here the ligand imposes a square planar geometry on the complex.